Thank you for that introduction. And yes, I come from a background of fluvial geomorphology, but lately I've been thinking a lot about BGI and how they change through time, and applying some of what we know about rivers and fluvial dynamics to thinking about the dynamics of BGI and what that means for their performance and their sustainability. But before we dive into that, because I'm new to a lot of you, first I just thought I'd tell you a little bit about where I'm coming from, and that's the world of rivers. And so this is produced by Aqueduct through the World Resource Institute. It's a global map of riverine flooding, as opposed to coastal flooding, right? And so just a little background of where I came from. I started my engineering career in Samoa, and this is an example of a flood that I experienced when I was there. And it shut down the entire town, the entire capital, but also the entire country. And I was stuck in my town for several weeks because we couldn't get through the roads. And while this was a challenging few weeks, the impacts of this flood went on for years and impacted crops and things for quite a while. Later on in my career, I worked in Vanuatu, and I took this picture where a bridge had washed out near a town, isolating groups of students who were no longer able to attend school, as well as just mobility of the local population there. I then worked in Southeast Asia. These are pictures I took in Bangkok, Thailand, and also in rural Vietnam, where you can see the monsoon season, the wet season, brings a lot of water and repetitive flooding that happens every year. And as I'm sure for any of you who have experienced a flood event or know someone that has, these waters are not clean. You don't want to go swimming in that water, right? I then went on to Afghanistan. Now, Afghanistan has had a lot of challenges, but on top of all of the challenges that war brings, they also have the highest rate of deaths per capita due to flooding. And that's largely in Kabul, where they've experienced this large population growth since the early 2000s. And the city has increased hugely in size, but the infrastructure hasn't been able to catch up. And it's created this really flashy system where you have a lot of flood-related deaths. I went on to work on a lot of projects and these other dots that I've had here, and I'm happy to talk to you about any of these projects or some of the other research mentioned in this over the next 3 months. Finally, I ended up in Philadelphia at Villanova. And here we have the exact same thing that we've seen all across the world. This challenge that unites a huge portion of the population getting around flooding. And it doesn't really matter if it's a wealthy country or if it's a poorer country with a lower GDP. As climate change is exacerbated, and flood events are exacerbated, this is a bigger and bigger challenge. And as our urban areas are growing, this challenge is going to continue to increase. Right now, for the first time ever, more than half of the world is urban. Half the world's population is urban. I have 2 little girls, they're 4 and 6, and by the time they're my age, almost 80% of the world's population is projected to be urban. This is exciting because it's a big challenge. And challenges for engineers are opportunities to advance science and knowledge. So while we have this big challenge, we also have exciting opportunities and new tools that we can use to start addressing these. Remote sensing. This is a project that I worked on in Freetown, Sierra Leone. They have a monsoon season that can be drastic, as you see the picture here. I started working on this right before the pandemic, and then no travel, no ability to go out and collect data. Instead, we were able to use remotely sensed data to accurately and efficiently predict the exact buildings that would flood in Freetown. So they were able to get relief to these areas pretty quickly, which was a really great thing that we're able to change this. We also have tools like artificial intelligence. We're in the data revolution, the 4th industrial revolution, and we can see the world differently than we've ever been able to see it. For those of you that are students, you're going to see the world in a way that I can only imagine right now. Data is going to change that. And tools like artificial intelligence and different machine learning tools are going to help enable that. Now, I need to caveat both of these things. They're exciting and we just want to run into them and use them for everything. However, like anything, there's a range of reasonable executions that we can use these tools for. And right now, there's a lot of excitement around both of these things, particularly I hear a lot about artificial intelligence. But it's easy to apply this and to divorce this from the science and the physics and end up in a place where your results maybe don't make sense and get yourself away from the scientific method. I think these are things that can help us explore and understand what's happening in science and the physical world more. But we really have to be careful about the way that they're applied. So another new exciting thing that's been happening over the past several decades, and really not just started in the past several decades, but taken off in the past several decades, is blue-green infrastructure, or what we in the US, we're gonna call it S&P's stormwater management practices, or BMP's best management practices, or GSI, green stormwater infrastructure. There are so many different names for this, and I apologize in advance if I use one of these names and it gets confusing. Realize that this is what I'm talking about, a nature-based solution. And in the United States, we're usually talking about this in relation to stormwater. So we have something called the Clean Water Act, and this piece of legislation said, all right, everybody, urban areas, get on the ball and clean up your stormwater. You have to do something. And this has become the most popular fix in response to the Clean Water Act. And as a result, this is becoming prolific across the United States. And in fact, in Philadelphia, almost 8,000, what we call GSI, have been implemented in just the past decade. 8,000. It's changed the way our city looks. It's changed the quality of our rivers. And it's changed a lot of other things too. There's a lot of co-benefits that are happening that we're not even accounting for. And we don't fully understand how these systems come in. So you students, this is your job. So figure it out, make the world better. We're all excited to see you do it anytime. But other cities across the US have this too. In New York City, in Portland, but we also see this in huge projects like China's Sponge City project that's massive. We see this here in Europe, in Zurich. This is an image that I found of a green roof. And this BGI, or nature-based solutions, they can look a lot of different ways, right? We can talk about tree planters or rain gardens, infiltration trenches, bioswales, all different kinds of things, but we have similar goals and objectives. It's just that we might be designing slightly differently depending on what our regulations or our focuses are. So, speaking the same language, when it comes to this type of infrastructure, it can be really challenging. We might be talking about the same thing, but just looking at it through a different lens and using a slightly different language. So a paper by Mastler et al. That came out in 2021, just last year, broke down some of these barriers. And they started breaking down the terminology for different types of green or blue-green infrastructure in terms of what the interest was. And so here you can see an example from green space planning and just the planning perspective of just putting green areas out there. And you have the year on the x-axis, in case you can't read it. And then on the y-axis, you have the number of publications that are occurring. So you can see from this green space planning, the interest in this is increasing up and up and up. You start thinking about this from an urban ecology perspective, you have more terms come in. Here you have your blue-green infrastructure. That's the more common term here, I believe. And you also have a few others, nature-based solutions, ecological infrastructure, urban forestry, ecosystem services, that you can start thinking from that lens. And this is even a more dramatic graph than the previous one. Until the mid-2000s, you really got very few publications on this. And when you think about this in terms of stormwater, here we have our BMPs, our best management practices, LID, low impact design, sponge cities, and you can look at the number of publications and see how this has exploded in recent decades. And there's a lot of work going on here. This is a relatively new type of infrastructure in the way that it's being so widely implemented. But one of the challenges is that because it's so new, we don't understand a lot about how these infrastructure change through time. Now, anecdotally from Philadelphia, I can tell you, they blew through their 20-year maintenance budget in 5 years. because it turns out that these systems, while they do have a low overhead, do have maintenance requirements. We'd all love to just set it and forget it, right? But that's really tough when you're thinking about the performance of these systems and what you want these systems to do and keeping them maintaining that performance through time. So how do these sites perform over time? These are open systems. We have things coming in, water, probably sediments, seeds, trash, litter coming in over time. And you also have things leaving. Because it's an open system, we know that there's probably some change occurring through this. So to understand more about this change, we said, let's think about data. And actually, we is VCRUS. So I'm part of a center, the Villanova Center for Resilient Water Systems at Villanova. And VCRUS was started by a guy who was here a few months ago, Rob Traver. And 20 years ago, Rob Traver started thinking about BGI. And he built something called the bioinfiltration trench, shown here in an image. And he started monitoring that with flow sensors and taking samples for water quality before and after storms and looking at the depth and the weather and keeping track of all of these different variables at the 5-minute scale for 20 years. That's a lot of data. But then we started getting other sites, and pretty soon we had 21 sites of different types of BGI all around the Metro Philadelphia area. Now this generates a lot of data. And I showed up to Villanova and it was really clunky because it's tough to get that much data. It's tough to QA/QC that data and make sure that it's all clean. So what we did is we built a novel data model called the Stormwater Infrastructure Data Model. It's based on Quasi's observational data model, which is used for hydraulic science in the US, and also similar versions of that are available here in Europe too. And it's a relational data model that allows us to take all of this data, and every observation has 21 pieces of metadata associated with it. So what time was this collected? Where was it collected? How was it collected? Was the storm or base flow? What was the detection limit for how you were collecting this? And it's all collected in these 21 different tables. And for every piece of this value, we have a controlled vocabulary. So we're using the same vocabulary every time. So now we can sort our data really efficiently and effectively. And now I can get 2 million data points in half of a second. So the fact that I have this data dating back to 2000 is no longer this onerous task to try to go get that data. I can now just go to the database in our server and get that data in a fraction of a second, which is pretty cool. And these are the types of things that we have to start thinking about if we're going to start looking at these systems at the large scale and also temporally large scale too. So when we start looking at the data, what do we see about how these work through time? Del Grosso et al. Looked at several GSI around the Virginia area, and they noticed that these were the main causes of failure and underperformance: sediment, blockages, debris, structural issues, erosion, bare spots, vegetation. Now I've put red boxes around all of the ones that are related in some way to sediments and debris coming in and erosion. Those transport processes associated with the water right on the surface. And so here I have a list of papers, and this is a list of papers talking about data and how the use of data can be used to highlight these different challenges and understanding how GSI and BGI change through time. All right, so now we have all of this data and all of these sites, and it's a lot to get through, so I'm not going to try to get through it all today, but we're going to talk about one specific site. So this specific project is the largest single BGI, GSI, green infrastructure project going on in the United States. This is in central Philadelphia. It's an interstate, 10-lane road, and this entire 10-lane road is going to be drained using completely nature-based solutions. That's it. They're putting in about 90 rain gardens. That's quite a lot. So Villanova has been brought on to advise on this. How do we make sure that these rain gardens last? They're spending a lot of money to put these in. So how do you make sure it's actually able to take all of that stormwater from 10 lanes of traffic through the entire city? So this will focus on one of those rain gardens, which we call SMPA, Stormwater Management Practice, because that's their language. And in that SMPA, we notice that there's a lot of sediment movement. It's moving around quite a bit. And I, as a fluvial geomorphologist, I started looking at this and I said, oh, that kind of looks like a river. Look how it meanders. I see rivers everywhere. Caterpillars, leaves, everything meanders, right? So at first they said, well, yeah, sediments move around. But yeah, maybe it's a river. And so we started thinking about the sediment transport dynamics and what was happening. And then we looked at the outlet of this, and we noticed that there had been a ruler put in to look at how much sediment was being deposited. And this is roughly 3.5 inches. That translates to about 7 centimeters of deposition that happened in just 3 years of this baby rain garden's life. So just in the first 3 years, it got 7 centimeters of deposition. What does that mean for the infiltration rates? What's that mean for the performance of this? Well, that's a great question. So we started looking at this and we used this 3-prong approach. We used thinking about it from a geomorphic perspective, a water resources perspective, and a geotechnical perspective. And we did a lot of field work and then lab work, and then started pairing this with fluvial models to treat it like a river to understand where the sediments were going through time. So our field testing, we did infiltration tests. This is the Saturo shown here. It lets us know what our KSAT is as the water is going into the ground. And then we took soil samples at all of these locations shown above me. We took samples that were at 0 to 15 centimeters, 15 to 30, and then 30 to 45. And then we took deeper core samples at these locations, the upstream and downstream locations, AU upstream and AD downstream here. Then we took we also did sediment sampling. This is called the dirt bag, not my term, it's the registered trademark for it. And this is collecting all of the sediment that's coming out through the inlet and into the rain garden. Of course, this is a geotextile, so the very fine material is leaving, but we were able to collect that through auto sampler and pair that together to get the full sediment load. We also did Lidar surveys. So this is our Lidar survey. Hopefully I always get nervous about videos during talks, but it looks like it's working. So through this Lidar survey, this was about 8 setups, took about 2 hours to do. And what Lidar allows us to do is we can use the reflectance, we could see where there's any topographic changes, of course. This is giving us accuracy to the millimeter level, but it's also allowing us potentially in the future to look at where clogging might be, where we're getting changes in vegetation, how much vegetation is changing over season to season, because we can use the reflectance to filter out what's vegetation and what's not. So there's a lot that we can do here. And even though the rendering isn't able to keep up with the accuracy, I hope that this gives you a feel for the type of information we're able to extract from Lidar. And it's kind of like you get a tour of the rain garden in 3 dimensions. So yeah, as you can see, you've got the highway deck up high, and the water comes in, it's got a whole lot of energy as it enters. That energy can be very erosive, but it's taking with it all of the sediment and the debris from the deck and coming down into the GSI. So we took all of our soil samples and we brought it into the laboratory. We started looking at the soil a little bit more to try to understand, is it changing? Is it staying the same? What's going on here? So we looked at our particle size distribution, the plasticity, the organic content, the density and the KSAT through hydraulic conductivity test, and also the soil water characteristic curves. So what did we find? How does this open system change through time? Well, in the case of this SMP with 7 centimeters of deposition in just 3 years, it didn't really change. You can see here in the particle distribution curves and the infiltration, this is just an example, but you don't have a lot of change that's happening. We know that this is changing. You can see the deposit, we can see the sediment coming in, we can see the erosion and the deposition, but the function isn't really changing. This is working out great, and that's great for SMPA, but a lot of these GSI need a lot of maintenance. A lot of them fail, to be honest. And so how do we make sure that they don't? Why is this one working but others aren't? What makes this one special? Just good luck? Probably not. So we started thinking about this a little bit more. We have this depositional layer on the top, and then we have this engineered surface. So if your depositional layer that's where the water is first meeting it, if you have something that's blocking the water at that level, then that's potentially affecting what you're doing. So when dam engineers thought about this in their tailings designs for like an earthen dam, they use different types of graded filters to make sure that the dam is stable, right? And so when you think about graded filters for an earthen dam that would be used for like mine tailings or something like that, there are two main criteria. We're thinking about retention of soil particles and also permeability to allow flow through. Seen from this image is taken from the US Bureau of Reclamation. So we don't want particles to pass and clog the filter through that. So Terazaki created this criteria back in the 1940s where you could look at your D15 of your media and also your sediment, or what they were using is their media and their filter, right? And your D85, and you could use that relationship to establish what would allow for retention and still allow for permeability. And so from that, we instead could think about this as our media of our BGI and our incoming sediments. And what's the appropriate relationship here where our incoming sediments aren't going to clog our media? It's going to allow our BGI to continue to function sustainably through time. So here, this is just an example that we've created where we have increasing grain size going towards the x-axis and the percent passing going upward on the y-axis. And so we started applying this idea to the soil samples that we had collected in the lab and thinking about what was just at the surface and that top 15 centimeters, and then what was lower and what happened. And so these are some of the results that we got. So here we have our measured surface samples, what's coming in through our sediment, right at the surface level there. And then we have our example filter that would allow flow through. So what's our ideal filter for these sediments that are right at the top? And then we paired that with our measured soil column. And you can see that the majority of our soil column fits really well in what our design media should be according to this criteria. Wow, that was lucky for us, right? And it also lines up with the codes, even though the codes aren't based on this. It just happens to fit quite well. There is a little portion here at the bottom that could limit your permeability over time, your permeability over time. But at this point, we're not seeing any issues, but it would be something to look through in the future. So for the most part, we're able to function really, really well. And what we found in addition to this is it's not necessarily just one portion of your particle size distribution. You're not just looking at your D50 or even just your D85 or just your D15. It's really how well sorted your full particle size distribution is to keep your media from clogging. So here's our example from SMPA, the rain garden that we were talking about. So here we've got our measured envelope shown in the darker shade here, and then our sediment that's compatible with SMPA. And then of the sediment that we collected, shown in the bar, the D50 shown in the bar going across the top. So you can see that we've seemingly happened in to a really compatible sediment. Well, that's great. We have this highway sediment, and we know that it lines up well with this media. But could we do this more efficiently? Could we do this in a more effective way? Are we over-designing? Or are the standards for our soil maybe what's causing some cases to fail and other cases to work out well, right? So do we need to be more specific in how we're designing this? So to understand if we do, we thought, well, let's understand what's actually coming into the system. What's an urban sediment look like? Nobody really knows because every urban area is different. These are a couple examples from some of our sites in Philadelphia. If you see me this summer looking in the gutters, I like to walk around and just look at urban sediments. And I've noticed that Zurich has some pretty clean streets, but I do see a lot of little fines along and some sand grain particles. And so So thinking about what this looks like, we started taking a lot of our own samples, but we also started trying to estimate this at the city scale. And so we went through some processes, and we have a couple papers that we've put out and some that are coming out that have looked at delineating all of the urban catchments for every single inlet in all of Philadelphia, and then trying to estimate how much sediment and litter and debris is going into each of those. And then what does that mean for the infrastructure that's there? Will it clog? Will it just clog up the drainage? How could it be mitigated? What type of infrastructure should you put in based on what type of risks are there? And then we started mining all of the literature that we could find to try to get sediment loads around the world. And so we've built on it a little bit more since this, but we started putting together different physiographic regions across the world, as well as different types of land cover and different stormwater managements, and breaking this down in as many ways as possible to see if we could see any trends. Also snow management, right? Some places use dirt for snow management, other places use different things. And so we go back to this graph of SMPA, and just the soil for SMPA, we're using that as an example. And what if you broke it down by different types of drainage basins instead? So using all of the information that we have, we can say highway sediment looks about like this based on the D50. And arterial streets or mixed use or parking lots looks something a little bit finer. So surface systems would be just like a parking lot system. And so we then paired that with what our compatible sediment was for SMPA. And so you can see now, if you're designing for a particle and particles that are coming off of a parking lot system, you're more at risk of clogging than you would be if you're thinking about a typical particle coming off of a highway, which we acknowledge can vary a lot, right? So if you're designing for different types of drainage areas, you might actually need to change the soil media that you're thinking about. And now we're very interested in the amount of stormwater coming off of the surface. That's what we've been thinking a lot about in the United States. However, if your media clogs, even if you're interested in other factors, it's still going to change the function of your system. So if you plant for one type of vegetation in your BGI, and then it clogs, your vegetation will either die or change. I guess either way you're changing, right? So we've seen cattails move in where there used to be shrubs and things of that nature. So it changes the function of what's happening in the system itself. Right. So then we said, well, how's the sediment really moving through the system? Is the whole system at risk, or is only part of the system at risk? Because what we saw at SMPA is that we're getting a lot of deposit at one end, a lot of erosion at other parts. And so do we need to think about maintain the entire SMP, or could we just think about part of it? Well, a few years ago, a student and I developed this backwater fluvial geomorphic model. And in that, we took into account the backwater hydraulics and how that was affecting shear stress and then the deposition of sediment in the backwater. So we started thinking about that model, and we figured out a way to apply it to SMPA. And when we applied it to SMPA, we could see areas of high and low shear stress. And we don't think that those numbers are particularly accurate, so I'll encourage you to just think about this as a gradient. And when we did, we could go out and look at areas and easily find areas of high deposition and high erosion. And so we realized by just changing the geometry of these systems, we can force the shear stress to change. And therefore, we're altering the hydraulics and forcing that sediment deposition to happen in different locations, right? So alter the hydraulics, change the shear stress, therefore alter your erosion and deposition patterns. So when you think about blowing through 20 years of funds in just 5 years, what if you didn't have to maintain this entire space? What if you just could make part of the space the sacrificial place where all of your junk goes and all of your fines? Because we could do that, especially now that we understand when this is going to clog and when it's a problem. So now we're trying to think more about the advection processes of sediment and fines as this is moving through the system. And once we understand where these fines are going, this is also going to allow us to understand more about the transport of pollutants into these systems. PAHs adhere to sediment, and they get transported through wet systems attached to sediment. And if we understand where this is being deposited, we can understand where some of those contaminants are. What about microplastics? Is it on the surface? Does it work its way into the soil? PFAS, PCBs, all of these things. What we have seen is that nitrogens and phosphates are staying fairly close to the surface. So this is the BTI, and we applied this idea of where shear stress was high and low in the BTI using a model called IRIC and paired with ArcHydro. And in doing that, we were able to look at these 5 points here and see just in the top 2 inches where this is an example of our nitrogen, our total nitrogen percent, where they're high. And in the areas in the basin, 4 and 5, where the water sits, you have a hard backwater hydraulics there, then you're getting a lot of deposition. 0.3, where you have relatively little inundation, you don't have very much nitrogen. And 0.1 and 0.2, where the water is moving the fastest and moving right around, then you're not getting very much nitrogen there too. Those are our erosive spots. So we've applied this, looking at the shear stress, and we applied this to fines and also to total phosphates, and we saw similar trends. This repetitive thing where you have a high shear stress, you're not getting a lot of phosphates, and you're not getting a lot of nutrients, and you're not getting a lot of fines. All your problems are happening in the bowl. And so we took from rivers and we applied it to GSI, but what if we then went the other way? Oh, sorry. This is just another example of showing the topography and the cross-section, so you can see where you have the biggest slope change and also the biggest shear stress change happening. So we took this idea of where we had high and low shear stresses and where we were seeing deposition of different particles and different nutrients, and we applied this to PAHs in a river. And this is Darby Creek, where we developed that backwater model years before, and then we came back to it with the same student, and he looked at it again with PAHs. And what we found is that the PAH concentrations in the channel where you had the most flow, and it's an urban channel syndrome, sediment starved, typically incised a bit, very few PAHs. But when you got to the banks, especially the higher banks, the PAHs really became present. Once you get out to the floodplain, where it's not being inundated as much, and the sediment that's getting out there is a good bit finer, your PAH levels started to drop off. And so we can think about this, about what's happening with the transport processes, and link that back to the pollutants. And I believe that even if we understand more, linking the surface processes to the infiltration in the soil column, we can understand the fate of some of these pollutants a lot deeper. Okay. So in conclusion, urban flooding's a real big, complicated mess. It's a big problem, but it's a great opportunity for us as engineers to understand and advance the science and engineering more. Infiltration rates at S&P-A through this project period are really great. They've maintained the same, but in understanding why they've maintained their rates while others haven't has allowed us a little bit more understanding of the restriction of sediments to the near surface to act like a granular filter and apply filter dam concepts. Testing is underway to evaluate the limits of this. So we're using falling head test right now to try to pick out the thresholds and actually rewrite the equations specific to media surfaces as opposed to thinking of it exclusively as filter dams. And then GSI morphology can be leveraged to help us have a more efficient and effective design accounting for erosion and deposition potential. And finally, this knowledge can be transferred to deepening our understanding of rivers and floodplains, especially in areas where we're concerned about the transport of different contaminants. This is the work of a whole lot of people. Dr. Kristen Sampelord, Dr. Bridget Wadzik, Dr. Rob Traver, Dr. Husseini, Dr. Zhu, Dr. Ampama, Dr. Kramer, and a slew of students that have contributed to this. As well as the funders, I must mention the Pennsylvania Department of Transportation and AECOM, Philadelphia's Water Department, the Pennsylvania Department of Environmental Protection, and also the National Science Foundation. And finally, I'll leave this slide here. This is picked out from several publications. And so these are a bunch of them. And I know I covered a lot of stuff and not a lot of detail, but I'm happy to go into more detail now or talk about it over the summer. Thank you.